You know, we're on the edge of a world that doesn't just watch us, but actually understands us. Think smart factories, autonomous cities. The promise of AI is literally everywhere. But there's this one huge problem holding that future back. A massive conflict that's being fought on two really critical fronts. Okay, let's get into it.
The ambition in the tech world right now is, well, it's just incredible. The goal isn't just to make AI smarter up in the cloud. It's to take all the power of a giant deep neural network and cram it right into the tiny battery-powered gadgets that are all around us. We're talking smart cameras, industrial sensors, you name it. The idea is to put real, actual intelligence right there at the source, at the very edge of the network. I mean, it sounds amazing, right? But if the goal is so clear, why isn't this our reality today? What's the holdup? Well, it turns out there's a massive gap between that dream and the cold, hard laws of physics. And this brings us to the first major battlefield. It's all about the impossible demands that AI makes on our hardware. There's this fundamental conflict between what these massive algorithms need and what tiny, low-power silicon can possibly give them. The dream, of course, is to have the whole AI model, the entire deep neural network, just running locally on that little IoT device. That would be super fast, totally private, and really efficient. But the computational juice and the battery power these models need, it's just way too much for a small device.
So in the real world, it's way more complicated. Researchers have found this huge roadblock that gets in the way of any simple solution, and it's got a name. They call it the structural barrier. So what on earth is that?
Okay, these two graphs show the problem perfectly. Take a look at the chart on the left. This is the ideal world, right? As you do more work on the device itself, that's the bottom axis. The energy you need to send data, the blue line, goes down. Makes perfect sense. But now look at the chart on the right. This is the crazy reality for AI. In those first few steps of processing, the amount of data actually explodes. It gets bigger. This creates that giant yellow hump you see, a huge spike in energy that makes it a terrible idea to split the workload anywhere in that zone.
So, how do you get past that? Well, that leads us to the software front. The battle here is all about making the algorithms themselves way smarter and a whole lot more efficient.
So the main strategy is something called split computing. The whole idea is to basically chop the AI model in two. The little IoT device does the first bit of thinking, and then it zips a compressed summary over to a big, powerful server to finish the job.
And this diagram just lays it out perfectly. You can see the AI's brain, the DNN, is literally split. Part A runs on the little local device, it chews on the raw data, and then sends a much smaller package over the network. Then part B, which is running on the server, takes that little package and figures out the final answer.
Now, to make this actually work, researchers came up with this really clever three-step strategy. First, you figure out where that data bottleneck is. Second, you actively force it to be more efficient. You shrink it. And third, you recover any accuracy you might have lost on the other end. Let's see how they do it. The real magic, the secret sauce, is in step 2. Instead of just living with that data explosion, you actively fight back. You use these advanced techniques, things with cool names like waist tightening, and this extreme data compression called one-bit quantization, to just forcefully crush the data at that split point, making it tiny enough to send without any trouble.
But wait, if you crush the data that much, doesn't it ruin the quality? That's where step 3 is so brilliant. The big server uses a special AI of its own, a quantization compensator network, or QCNet, to intelligently rebuild the information. It's like it knows exactly how the data was squeezed and can perfectly unsqueeze it, restoring the accuracy without ever bothering the little device. It's just a genius way to separate efficiency from performance.
So problem solved, right? We've got this incredible software fix. Well, not so fast, because even the smartest algorithm in the world is totally useless if the device it's running on isn't reliable, or if it's just too expensive to deploy in the first place.
And this brings us to the other front of our war, the hardware. And this is not a battle of algorithms. This is a battle of power, of uptime, and of cold, hard economics. Here is the absolute heart of the issue, and the startup, A-Chip, put it perfectly. People want this specialized AI at the edge, but the economics just don't work. I mean, think about it. If you have a factory with thousands of sensors, and even a few of them fail, your whole system could just grind to a halt. Deploying and managing these things at scale is a nightmare.
So AI chip's strategy isn't to just build a faster AI chip. As they say right here, they're not competing on raw performance, that's TOPS, trillions of operations per second. No, they're competing on deployability. They're obsessed with making it practical and affordable to actually get these devices out into the world and keep them running.
Their solution is a completely different kind of chip, the AI-PMC, the AI Embedded Power Management Controller. It's not the main brain doing the AI thinking, it's the brain that manages the power. It sits right next to the main processor and intelligently handles things like power-up sequences, uptime, and recovering from faults. It basically turns power itself into something you can control, which is absolutely critical for making huge fleets of devices reliable and affordable.
Okay, so now we have two totally different solutions, both aimed at the same huge problem. One is attacking the software, the other is attacking the hardware. A real victory, though, that only happens when you bring them both together. And this slide just lays it all out. On the software front, the tactic is to shrink the AI model. The weapons are things like quantization and pruning, and the goal is to cut down the energy and the lag for a single task. Now, on the hardware front, the tactic is to govern the device's power using that AI-PMC. Here, the goal is to maximize the deployability and reliability of the whole fleet. See, they're not competing with each other, they're perfectly complementary.
And that brings us to the biggest takeaway from all of this. To truly unlock AI everywhere, you can't just pick one battle to fight. You have to win on both fronts. You need these incredibly clever, efficient algorithms, and they have to be running on hardware that is fundamentally reliable, governable, and economically scalable.
So when you combine these breakthroughs in software and hardware, you get way more than just a smarter device. You get a reliable, scalable foundation for intelligence to be everywhere. So the real question isn't if we can put a supercomputer on a thumbnail, but when we do. What incredible new things is that going to unlock for all of us?